Space is often described as cold, but that simple word does not fully explain what space really is. Because space is not cold like winter. It is not cold like ice. It is not cold like standing outside in the middle of the night. Space is something far more terrifying. It is an endless emptiness where heat has almost nowhere to go. And yet, if you are far from a star, warmth slowly disappears until everything becomes silent, frozen, and lifeless. Out there is no air to carry heat, no atmosphere to protect you, no warm ground beneath your feet, no clouds, no wind, no shelter, and no world around you. Only darkness. A spacecraft floating in deep space can be burned by sunlight on one side, while the other side freezes in shadow. An astronaut exposed to space would not simply feel cold the way we understand it on Earth. The danger would be stranger, more silent, more absolute, because in space, temperature does not behave the way it does here. Tonight, on Stellar Depth, we explore the terrifying truth about how cold space really is. From the frozen darkness between planets, to the shadowed craters of the moon, to the deep cosmic background left behind by the birth of the universe, we will discover why space is not just empty, it is freezing. And the deeper you travel into it, the more you understand that warmth is not normal in the universe. Warmth is rare. Warmth is fragile. Warmth is Earth. On Earth, cold is something we understand through contact. You touch ice, and your skin pulls away. You step outside in winter, and the air bites your face. You open a freezer, and you feel the invisible wave of cold rolling over your hands. Cold, for us, is usually something that moves through air. It surrounds us. It enters our clothes. It pushes against our skin. It makes our fingers stiff, our breath visible, and our bodies search desperately for warmth. But space is not like that. Space has almost no air at all. And that is where the truth becomes strange. Because when people imagine being exposed to space, they often picture someone freezing instantly, as if space itself is a giant block of ice waiting to swallow anything warm. But space does not freeze you the way ice freezes you. It is much more silent than that. On Earth, cold reaches you quickly because air, water, and solid surfaces can carry heat away from your body. If you fall into freezing water, heat leaves you extremely fast, because water conducts heat far better than air. If you touch a metal pole in winter, heat flows from your skin into the metal. If you stand in cold wind, moving air strips warmth from your body again and again. This is how cold attacks us here. Through matter, through things touching us, surrounding us, or flowing past us. But in space, there is almost nothing to touch you. No thick atmosphere, no wind, no ocean, no ground, no clouds, no rain, no snow, just vacuum. A near-empty darkness where particles are so spread apart that there is almost no material to carry heat away by contact. So if a warm object is floating in space, it does not lose heat the same way a warm object loses heat on Earth. It cannot give its heat to air, because there is no air. It cannot feel wind, because there is no wind. It cannot pass warmth into the ground, because there is no ground. Instead, it loses heat mainly by radiation. It gives off infrared energy slowly, sending its warmth away as light the human eye cannot see. This means space is freezing, but not in the simple way we imagine. It is not a cold room. It is an emptiness where heat has almost nowhere to go except out into the dark, photon by photon, wave by wave, over time. And that makes space one of the most disturbing environments in the universe, because it does not always kill with speed. Sometimes it kills by isolation. A warm body in deep space becomes like a candle placed in an infinite black cathedral. The flame may still burn for a while, but nothing around it gives warmth back. No walls hold the heat. No air wraps around it. No world protects it. The warmth simply escapes, slowly, silently, forever. This is why the question, how cold is space, is more complicated than it sounds. Temperature on Earth feels simple because everything around us has substance. Air has temperature. Water has temperature. Soil has temperature. Your chair, your floor, your blanket, your window, your skin, everything is constantly exchanging heat. But space is mostly emptiness. So what does it mean for emptiness to be cold? If there is almost nothing there, what exactly has a temperature? This is where space becomes difficult for the human mind. A vacuum itself does not feel cold in the same way air feels cold. But objects in that vacuum can become extremely cold if they are not receiving enough heat from a star or another source. Far from sunlight, far from planets, far from anything warm, an object can radiate away its heat and fall toward the deep background temperature of the universe. That background is incredibly cold. Not exactly absolute zero, but close enough to feel almost impossible from a human point of view. The universe still carries a faint leftover glow from its earliest history, a weak microwave radiation spread across all of space. It is the cooled remains of the early hot universe. Today, it gives deep space a temperature of only a few degrees above absolute zero. Absolute zero is the point where thermal motion reaches its lowest possible limit. It is not just very cold, it is the edge of cold itself, and deep space comes frighteningly close. This means that far away from stars, planets, and warm dust, the universe is not just dark, it is nearly frozen at a cosmic level. But near a star, everything changes. This is another terrifying truth about space. It can freeze and burn at the same time. Near Earth, sunlight is powerful. If an object in space faces the sun directly, it can become extremely hot, but the side facing away from the sun can become extremely cold. Without an atmosphere to spread the heat around, temperature differences can become violent. On Earth, our atmosphere softens extremes. It moves heat, it carries warmth from one place to another. It scatters sunlight. It traps some infrared energy. It gives us weather, wind, clouds, and climate. Without it, sunlight and shadow become two different worlds. This is why the moon has such extreme temperatures. In sunlight, the lunar surface can become hotter than boiling water. In darkness, it can fall far below anything humans could survive without protection. The moon is close to Earth. It receives the same sun we do. And yet its surface can shift between brutal heat and brutal cold because it has no thick atmosphere to protect it. Now imagine deeper space. Imagine moving away from Earth, away from the moon, away from the protective systems that make life possible. The sun slowly shrinks behind you. Its warmth becomes weaker. Its light still travels across the darkness, but every kilometer makes it less intense. Eventually, the sun becomes less like a source of life and more like a bright memory. Out there, cold is not just a temperature. It is the natural state of everything. Most of the universe is not warm. Most of the universe is not comfortable. Most of the universe is not like Earth. Earth is the exception. A small warm island floating inside a cosmic ocean of darkness. We live so close to warmth that we forget how rare it is. We wake up under an atmosphere that holds heat against the planet. We walk on ground warmed by sunlight. We drink liquid water. We breathe air that is not instantly fatal. We sleep in rooms where walls, blankets, and bodies exchange heat gently through the night. Nothing about this is normal in the wider universe. It only feels normal because it is all we have ever known. The human body was built inside this softness. Our cells function within a narrow range of temperatures. Our blood must remain warm enough to flow properly. Our organs depend on steady internal conditions. Our brains, muscles, nerves, and hearts exist because Earth keeps the environment within survivable limits. Take that body into space without protection, and it enters a realm it was never meant to experience. But again, the danger is not the movie version. An astronaut exposed to vacuum would not instantly turn into a block of ice. The more immediate dangers would involve lack of pressure and oxygen. The body depends on atmospheric pressure to keep fluids stable and lungs functioning. Without breathable air, consciousness would be lost quickly. Freezing would not be the first problem, but cold would still be waiting. Once exposed, the body would no longer receive warmth from air or surroundings. It would radiate heat into the vacuum. Moisture on exposed surfaces could cool rapidly. In shadow, with no sunlight, the body would steadily lose warmth into the dark. The terrifying part is not instant freezing. It is that space removes every natural support your body expects. No air pressure, no oxygen, no warmth from the environment, no protective sky, no ground beneath you, no sound carrying through the vacuum. Even screaming would not travel through space the way it does on Earth, because sound needs a medium. Without air, the universe outside would remain silent. That silence is part of the cold, not physically, but emotionally. Cold on Earth often has sound with it. Wind through trees, snow under boots, rain against windows, water cracking into ice. But in space, cold has no voice. It is not a storm. It is not a blizzard. It is not a frozen mountain. It is absence. The absence of air, the absence of shelter, the absence of contact, the absence of anything that cares whether you remain warm. And this absence shapes every spacecraft ever built. A spacecraft is not only a vehicle, it is a thermal machine. It must control heat constantly. It must keep humans warm enough to live, but also prevent equipment from overheating. This is harder than it sounds, because in space there is no easy way to dump unwanted heat. On Earth, a machine can release heat into surrounding air. A car engine uses radiators and airflow. A laptop releases heat into the room. Your body sweats, and air helps evaporation carry heat away. In space, heat management becomes one of the great engineering challenges. A spacecraft must use radiators to emit heat away as infrared radiation. It must use insulation to prevent heat from escaping too quickly. It must use heaters to protect fuel lines, batteries, electronics, and instruments from freezing. It must carefully balance sunlight, shadow, internal power, and waste heat. Every part of the spacecraft is fighting a different thermal battle. One section may be too hot, another may be too cold. One instrument may need cooling, another may need heating. Space does not give one simple temperature, it gives extremes. A spacecraft near Earth can pass in and out of sunlight roughly every orbit if it is circling the planet. It may spend time under direct solar radiation, then suddenly enter Earth's shadow. The surface temperature of the spacecraft can swing dramatically. Without thermal control, materials can expand and contract again and again, stressing the structure over time. This is why spacecraft are often wrapped in reflective insulation. The gold or silver layers seen on many spacecraft are not decoration. They are part of survival. They help control radiation, reflect sunlight, and reduce heat loss. Thermal control is invisible drama. No flames, no explosions, no dramatic movement. Just the constant struggle to keep matter at the right temperature in a universe that offers no comfort. And the farther missions go, the harder this becomes. Near the Sun, the problem is too much heat. Far from the Sun, the problem becomes too little. A probe travelling toward Mercury must survive brutal sunlight. A spacecraft travelling toward Jupiter, Saturn, Uranus, or Neptune must survive weaker sunlight and deeper cold. Solar panels become less effective as distance increases. Instruments need heaters. Batteries need protection. Fuel can freeze. Moving parts can become stiff. Cold is not just uncomfortable for machines. It changes them. Metals contract. Seals can fail. Lubricants can thicken or break down. Electronics can stop behaving properly. Batteries can lose performance. Pipes can freeze. Sensors can drift. A spacecraft can be destroyed not by impact, not by radiation, not by a dramatic catastrophe, but by being unable to stay within the narrow thermal range its systems require. This is one of the quiet truths of exploration. Every robot we send into deep space is a small rebellion against cold. Every probe that survives past Mars, every lander that endures a lunar night, every spacecraft that keeps transmitting from the outer solar system is doing something extraordinary. It is carrying warmth and order into a universe that prefers darkness and decay. The outer solar system shows this clearly. Beyond Mars, the sun becomes weaker. Beyond Jupiter, it is weaker still. By the time we reach Saturn, Uranus, and Neptune, sunlight is only a pale fraction of what Earth receives. Those worlds are stunning, mysterious, and beautiful, but they exist in a realm of cold that feels almost impossible. Saturn's moon Titan is wrapped in a thick atmosphere, but its surface is unimaginably cold by human standards. Methane and ethane can exist there as liquids, forming lakes and seas under an orange sky. It is a world with weather, clouds, and shorelines, but not water shorelines like Earth. It is a frozen chemical mirror of our planet, showing what happens when complexity exists far from warmth. Farther out, Neptune receives so little sunlight that midday there would feel like deep twilight compared with Earth. And beyond Neptune, countless icy bodies drift in the darkness. Pluto, comets, dwarf planets, frozen fragments from the early solar system, all moving slowly through a weak, distant light. These worlds are not dead because they are ugly. They are dead because warmth is missing. Energy is missing. Liquid water is difficult to keep stable. Chemistry slows. Atmospheres freeze or escape. Surfaces become ancient, brittle, and silent. Cold preserves them like cosmic fossils. A crater can remain unchanged for millions or billions of years. Ice can hold ancient chemicals from the birth of the solar system. A frozen world can become a memory storage device, keeping records of events that Earth has long erased through weather, oceans, plate tectonics, and life. In this way, cold is not only destructive, it is preservative. It stops change. It slows reactions. It keeps old things old. But for life as we know it, this is a terrible bargain. Life needs movement. Liquid, flow, exchange, heat, energy. Too much heat can destroy life, but too little can pause it into silence. Earth survives because it sits in the balance. Not too hot, not too cold. Protected by atmosphere. Warmed by sunlight. Stabilized by oceans. Held by gravity. Alive with cycles. When we ask how cold space is, we are really asking something deeper. We are asking why Earth is warm. Why our planet did not become another frozen rock. Why our oceans remained liquid. Why our atmosphere stayed thick enough to protect us. Why sunlight arrived with the right strength. Why warmth became stable long enough for cells to form, evolve, and eventually wonder about the cold beyond the sky. This is why space feels terrifying, because it reveals that life is not surrounded by comfort. Life is surrounded by hostility. The warmth we experience every day is a narrow exception inside a freezing universe. And once you understand that, even an ordinary evening on Earth begins to feel different. The air in your room is not just air, it is protection. The blanket around you is not just fabric. It is part of a long human fight against cold. The walls around you are not just walls. They are a small shelter against a universe that would drain warmth away without hesitation. Outside your window, beyond the clouds, beyond the atmosphere, beyond the blue glow of Earth, there is a darkness so cold that almost everything we know would fail inside it. And yet, here you are, warm, breathing, held by gravity, protected by a world that turns quietly beneath the sun. Space is freezing. But perhaps the most terrifying truth is not simply that the universe is cold. It is that warmth exists at all. The deeper you think about cold in space, the more you realize that temperature is not one simple thing. On Earth, temperature feels personal. A summer afternoon feels warm because the air touches your skin. A winter morning feels cold because the air pulls heat away. A hot road burns your feet because solid ground transfers energy into your body. A frozen lake feels deadly because water steals warmth with terrifying speed. Everything around us teaches the body what temperature means. But space does not teach in that familiar way. Space is almost empty. And because it is almost empty, it behaves less like a place and more like a condition. A condition where heat is not shared easily. A condition where light can burn you from one direction while darkness drains you from another. A condition where an object can be exposed to the sun and yet remain only one shadow away from deep freezing. This is why spacecraft do not simply need engines and computers. They need thermal balance. They need to survive the invisible war between heat and cold. Every spacecraft is born on a warm planet, assembled in buildings filled with air, touched by human hands, tested under controlled conditions, then launched into an environment where nothing behaves the same way again. Once outside Earth's atmosphere, the spacecraft enters a world without weather, but full of extremes. There is no breeze to cool a hot surface, no air to spread warmth from one side to another, no atmosphere to soften sunlight, no blue sky to scatter radiation, no clouds to shade it gently. The spacecraft is suddenly alone with the sun, the vacuum, and its own internal heat. This creates a strange problem. In space, overheating can be just as dangerous as freezing. A satellite in direct sunlight can absorb intense energy. Its outer surfaces may become very hot. Electronics inside may generate their own heat. Batteries, computers, transmitters, motors, and instruments all release warmth while they operate. On Earth, unwanted heat can escape into surrounding air. In space, it cannot. The spacecraft must radiate that heat away into the blackness. This is slow, delicate, and difficult. At the same time, parts of the same spacecraft may be sitting in shadow, losing heat and dropping toward dangerous cold. So engineers must design a machine that can handle both extremes at once. One side may need protection from sunlight. Another side may need heaters. Some components must be insulated. Others must be connected to radiators. Some instruments must be cooled very precisely. Others must be kept warm enough to function. This is not a minor detail. This is survival. A spacecraft that becomes too hot can fail. A spacecraft that becomes too cold can fail. And in space, either failure can happen silently. There may be no explosion, no dramatic fireball, no visible disaster, just a component drifting outside its safe temperature range until it stops working. A battery loses capacity. A valve refuses to open. A fuel line freezes. A sensor begins giving false readings. A computer resets. A camera lens distorts. A fragile material cracks after repeated expansion and contraction. Cold does not need to be loud to be deadly. It only needs time. This is why spacecraft are often covered in layered insulation. Those shiny blankets seen on probes, satellites, and landers may look fragile, almost like metallic foil, but they are deeply important. They help control how much heat enters and leaves the spacecraft. They are not there to look futuristic. They are there because the universe is hostile to temperature stability. A spacecraft is a small island of order in a place where order is difficult to maintain. And nowhere is this clearer than in orbit around Earth. From the surface, Earth seems safely warm and protective, but just a few hundred kilometers above us, the environment already becomes extreme. A spacecraft orbiting Earth can move from sunlight into darkness again and again. In one part of its orbit, the sun strikes it directly. Soon after, it enters Earth's shadow and loses that light. Then sunlight returns. This cycle repeats. Hot, cold, hot, over and over. The outside of the spacecraft expands and contracts. Materials respond. Coatings age. Thermal systems adjust constantly. The crew inside, if there is one, may feel comfortable, but only because machines are working every second to keep the environment stable. The comfort is artificial, and that is one of the most important truths about living in space. Nothing comfortable happens naturally there. Warm air must be produced. Humidity must be controlled. Carbon dioxide must be removed. Water must be recycled. Temperature must be managed. Pressure must be maintained. Heat must be moved from places where it is dangerous to places where it can be released. Inside a spacecraft, warmth is not a background condition. It is a system. It is built, monitored, protected, repaired. The crew may float through a cabin wearing ordinary clothes, speaking calmly, eating, sleeping, and working as if they are inside a normal room. But that normal room is surrounded by vacuum. The walls are thin compared with the vastness outside. Beyond them is an environment where the human body has no natural defense. This makes the warmth inside a spacecraft feel almost miraculous. It is a tiny pocket of Earth carried into a place that has no Earth-like qualities. A spacecraft is not just traveling through space. It is refusing space. It is saying, inside this shell, there will be air, pressure, light, and warmth. Outside, there is none of that. And the difference between those two realities may be only a few centimeters of material. That thought becomes even more haunting when we imagine a spacesuit. A spacesuit is one of the most extraordinary survival machines humans have ever created. It looks like clothing, but it is closer to a personal spacecraft shaped around a body. It must provide oxygen. It must hold pressure. It must remove carbon dioxide. It must allow movement. It must protect against micrometeoroids. It must manage temperature. And temperature management is one of its hardest jobs. An astronaut working in sunlight can become too hot because the body produces heat through movement. The suit must remove that heat, or the astronaut would overheat. But if the astronaut moves into shadow, the same environment can become dangerously cold, so the suit must protect against both. This is why spacewalks are not simple walks. They are controlled operations inside an extreme thermal environment. The astronaut is not merely outside. They are separated from fatal conditions by layers of engineering. Every glove, every seal, every hose, every cooling tube matters. On Earth, if your hands become cold, you can put them in your pockets. If you feel hot, you can open a window. If your clothes are uncomfortable, you can change them. In space, comfort is designed before launch, and if something fails, the astronaut cannot improvise easily. The suit is life. This gives space cold a different emotional meaning. It is not like cold on a mountain, where the environment is harsh but still part of Earth. It is not like polar night, where the air is freezing but breathable with the right protection. Space cold comes with vacuum, with radiation, with silence, with no pressure, with no natural rescue. It is part of a complete absence of Earth. And yet, space is not uniformly cold. This is where it becomes even stranger. Around planets, moons, stars, and dust clouds, temperatures can vary wildly. Some regions are heated by sunlight. Some are warmed by internal geological activity. Some are cooled by endless darkness. Some are protected by atmospheres. Others are exposed directly to space. The universe is not one freezer. It is a landscape of thermal extremes. Mercury, for example, orbits very close to the Sun. Its day side can become brutally hot, but because it has almost no atmosphere to spread heat, its night side can become extremely cold. One world contains both extremes, divided by sunlight and shadow. This is not how Earth behaves. Our atmosphere and oceans move heat around. They smooth the planet's temperature. They prevent the day side from becoming impossibly hot, and the night side from freezing instantly. Earth is wrapped in balance. Mercury is not. The moon shows a similar lesson closer to home. During the lunar day, sunlight bakes the surface. During the lunar night, temperatures plunge. In permanently shadowed craters near the lunar poles, regions can remain incredibly cold for immense periods of time. Some of these shadowed places may preserve water ice because sunlight almost never reaches them. These craters are like natural cold traps, silent pockets where ancient ice can survive because heat rarely arrives. That idea is beautiful and unsettling at the same time. On Earth, shadow is temporary. The sun rises. Warmth returns. But on certain parts of the moon, shadow can last for millions or billions of years. Imagine darkness that does not end. A place that has not seen sunlight since before human beings existed. A cold so stable that it preserves traces of ancient cosmic history. This is the kind of cold space can create. Not just winter, permanent absence. Farther from the sun, this becomes even more dramatic. Mars is cold, but it is still relatively close compared with the outer planets. It has seasons, polar ice caps, dust storms, and an atmosphere, though very thin. It is a cold desert world where temperatures can fall far below what humans could survive without protection. but Mars still feels almost familiar compared with the realms beyond. Move outward to Jupiter, and sunlight weakens greatly. Jupiter itself is not simply a frozen ball, because it has internal heat and a massive atmosphere full of violent storms. But its moons live in a colder region of the solar system. Europa, Ganymede and Callisto are icy worlds. Their surfaces are frozen hard under weak sunlight, yet beneath some of that ice, there may be hidden oceans kept warm by tidal forces and internal energy. This is one of the most fascinating contradictions in the solar system. A world can be frozen on the outside and still hold liquid water below. Cold does not always mean dead. It can also mean hidden. Europa's icy shell may cover a dark ocean. Enceladus, a moon of Saturn, releases plumes of water vapor and ice from beneath its surface. These worlds remind us that warmth can exist in secret, protected under layers of ice far from the sun. This changes the way we think about cold. Cold can seal life away from the surface. Cold can protect underground oceans. Cold can create barriers that hide chemistry from direct view. The most interesting places in the outer solar system may not be warm on the outside. They may be worlds where warmth is trapped inside. But for humans, reaching and surviving there would be extraordinarily difficult. A spacecraft near Saturn receives only a small fraction of the sunlight Earth receives. Solar energy becomes weak. Communication delays grow. Temperatures are brutal. Machines must carry heaters. Landers must survive surfaces colder than anything humans experience naturally. Saturn's moon Titan is especially strange. It has a thick atmosphere and weather, but it is deeply cold. Its lakes and seas are not made of liquid water. They are made of hydrocarbons, like methane and ethane. Water ice on Titan behaves almost like rock because the temperature is so low. Imagine a world where water is not soft, flowing, and life-giving on the surface. It is stone. That is what cold can do. It can change the meaning of materials. On Earth, water is movement. On Titan, water ice can become landscape. On Earth, methane is a gas. On Titan, methane can fall like rain and collect in lakes. Temperature decides what reality looks like. The same chemical can be gas, liquid, or solid depending on heat. So when we travel through the solar system, we are also traveling through different versions of matter. Closer to the sun, substances evaporate. Farther away, they freeze. In the cold outer regions, chemistry slows into unfamiliar forms. This is one reason the outer solar system feels almost alien, even though it belongs to our own sun. It is not just far away, it is ruled by a different thermal logic. Worlds there are shaped by ice, darkness, and faint light. Their surfaces preserve scars from ancient impacts. Their atmospheres, if they have them, behave in strange ways. Their moons may hide oceans under frozen crusts. Their landscapes may remain unchanged for longer than entire civilizations exist on Earth. Cold stretches time. It slows erosion. It slows chemistry. It preserves. A frozen surface can remember the early solar system more clearly than Earth can, because Earth is too alive to keep its old face. Our planet recycles itself. Wind, rain, oceans, volcanoes, life, and plate tectonics constantly reshape it. Earth forgets by changing. Cold worlds remember by staying still. This is why scientists are so interested in icy bodies, comets, and distant dwarf planets. They may contain materials left over from the solar system's birth. They are cold storage for cosmic history. But what preserves history can also resist life. Life needs energy gradients. It needs chemistry that moves. It needs liquids, reactions, exchange, and renewal. Cold can slow all of this almost to silence. A frozen world may be ancient, beautiful, and scientifically priceless, but still nearly impossible for humans to inhabit without massive artificial support. This returns us to the central truth. Space is not simply cold because the temperature is low. Space is cold because warmth is rare, fragile, and local. A planet is warm only if conditions allow it. A spacecraft is warm only if systems maintain it. A body is warm only if biology continues producing heat, and the environment does not steal it too quickly. A moon may hide warmth only if gravity or internal forces protect it. Nothing guarantees warmth. Earth makes warmth feel normal, because we live inside a natural thermal miracle. The sun provides energy. The atmosphere holds enough heat. The oceans store and distribute warmth. The ground releases it slowly. Clouds reflect and trap radiation. Life itself participates in the balance. Even your body is part of this system. You eat food that ultimately came from sunlight. Your cells release energy. Your blood moves heat through you. Your skin regulates loss. Your breath carries warmth into the air. You are a warm creature because Earth is a warm world. Remove Earth and your warmth becomes something that must be defended. That is why cold space feels so terrifying in a documentary like this. It forces us to see warmth not as a default, but as a fragile achievement. The universe does not owe us comfort. The universe is mostly dark, thin, silent, and cold. Warmth appears in islands, near stars, inside planets, beneath icy crusts, in living bodies, in spacecraft cabins, in the glow of machines fighting against the void. Every warm place is temporary unless something keeps feeding it energy. A fire dies without fuel. A planet freezes without a star or internal heat. A spacecraft dies without power. A body cools when life ends. Warmth must be maintained. Cold waits. And perhaps that is the most haunting part. Cold does not need to chase anything. It is already there, surrounding every warm object, every living system, every fragile shelter humanity sends beyond Earth. The moment energy stops flowing, the balance begins to fail. Lights dim. Metal cools. Air temperature drops. Water freezes. Systems shut down. Motion slows. The universe returns things to stillness. This is why, when we look up at the night sky, we are not looking at a peaceful emptiness. We are looking at an ocean of mere silence, where warmth exists only in rare places and only for limited times. The stars are fires. The planets are experiments. The moons are frozen archives. The spacecraft are temporary sparks. And Earth is the warmest truth we know. A blue world wrapped in air holding oceans beneath sunlight, keeping billions of living bodies within the narrow range where life can continue. Space is freezing. But Part 2 teaches us something even more unsettling. Cold is not just out there. Cold is the universe's default. Warmth is the exception. And for now, Earth is the exception that is holding us alive. There is a place in space where cold becomes almost permanent. Not because it is far beyond the solar system, not because it belongs to another galaxy, but because sunlight cannot reach it. On Earth, shadow is temporary. A mountain blocks the sun for a few hours, then the light moves. A room becomes dark at night, then morning returns through the window. Even the coldest winter landscape eventually receives sunrise again. But on certain worlds, without atmospheres, without weather, and without Earth's gentle cycles, shadow can become something far more extreme. It can become ancient. It can become a place where heat almost never arrives. The moon gives us one of the closest examples. From Earth, the moon looks calm and familiar. It rises above cities, oceans, deserts, and sleeping houses. It glows softly in the night sky, almost gentle. For thousands of years, humans have looked at it as a symbol of beauty, time, mystery, and silence. But the moon is not gentle. It is an airless world exposed directly to space. There is no thick atmosphere to spread warmth, no clouds to soften sunlight, no wind to carry heat, no ocean to store energy, no living soil to hold moisture and moderate temperature. The lunar surface is ruled by sunlight and shadow. Where sunlight falls, the ground can become extremely hot. Where darkness remains, the temperature can collapse into deep cold. And near the moon's poles, something extraordinary happens. Because of the moon's slight tilt, some craters near the north and south poles contain regions that sunlight may never directly touch. Their floors sit in permanent shadow. The sun stays low near the horizon, its rays blocked by crater walls that act like ancient barriers against warmth. These places are called permanently shadowed regions, but that name feels too calm for what they really are. They are some of the coldest places in the inner solar system, dark pockets carved into the moon, hidden from sunlight for millions, perhaps billions of years. Imagine standing at the edge of such a crater. Above you, the sky is not blue, it is black. There is no air to scatter sunlight. The sun may hover low near the horizon, bright and sharp, but its light cannot reach the crater floor below. Inside that darkness, there is no sunrise waiting, no dawn slowly approaching, no warm season coming after a long night, only stillness. The cold there is not like night on Earth. It is older than civilizations, older than languages, older than every city ever built. A patch of lunar ground in permanent shadow may have remained dark since before humans existed, before mammals ruled Earth, before forests took their modern forms, perhaps even before many of the familiar features of our planet's surface had changed into what we know today. That kind of darkness is difficult to imagine. We are used to darkness as a pause. On the moon, darkness can be a geological condition. And inside those cold shadows, something precious may survive. Water ice. This is one of the great reasons scientists care about permanently shadowed lunar craters. If water molecules arrive there through comet impacts, asteroid impacts, solar wind interactions, or other processes, they may become trapped. In sunlight, they would escape or be broken apart over time. But in permanent shadow, the cold can hold them in place. The crater becomes a cold trap, a natural freezer without machinery, a vault in the moon. And this changes the moon from a dead grey world into something more complicated. It may not have rivers, oceans, or rain, but it may preserve hidden ice in the places where sunlight never reaches. That ice could matter greatly for future human exploration. Water is life support. Water can be split into hydrogen and oxygen. Oxygen can help astronauts breathe. Hydrogen and oxygen can become rocket propellant. Ice on the moon could one day support missions, habitats, fuel stations, or deeper journeys into space. But the same cold that preserves the ice also makes reaching it dangerous. A permanently shadowed crater is not a welcoming storage room. It is a place of darkness, extreme cold, uneven terrain, and communication difficulty. Machines sent into such regions must survive temperatures that challenge electronics, batteries, moving parts, cameras, and sensors. Solar power becomes difficult or useless without direct sunlight. Rovers may need special heaters, nuclear power, or cables extending from sunlit ridges. Even light itself becomes a resource. A rover descending into a shadowed crater would not simply drive into darkness. It would drive into an environment where every watt of power matters. Its wheels would touch ground that may have been frozen for an unimaginable length of time. Its cameras would need artificial lighting. Its systems would fight cold every second. The machine would be exploring not only the moon, but the physical meaning of absence. Absence of air, absence of warmth, absence of change. And the moon is close, only a few days away from Earth by spacecraft. If such cold exists on our nearest neighbour, then the deeper solar system becomes even more haunting. Cold traps are not limited to the moon. Any world with deep shadows, weak atmosphere, or distant sunlight can preserve places of extreme cold. Mercury, despite being the closest planet to the Sun, also has shadowed polar craters that can hold ice. That sounds impossible at first. Mercury orbits near the Sun, where daylight can be brutally hot. But again, space does not behave like Earth. Without a thick atmosphere, heat does not easily move from sunlit regions into shadowed ones. A crater floor that never sees sunlight can remain cold even on a planet so close to the Sun. This is one of the strangest lessons in planetary science. A world can be roasted and frozen at the same time. Location matters. Angle matters. Shadow matters. Atmosphere matters. Temperature is not simply about distance from the Sun. It is about whether energy arrives, whether it stays, and whether it can move. That is why space cold is not only a number, it is a geometry. The shape of a crater can decide whether ice survives. The tilt of a planet can decide where sunlight falls. The presence of air can decide whether heat spreads. The darkness of a surface can decide how much energy is absorbed. The brightness of ice can decide how much sunlight is reflected back into space. Every world is a thermal puzzle, and every puzzle tells us something about survival. On Earth, nature solves many of these problems for us automatically. Our atmosphere acts like a blanket, but not a simple one. It allows sunlight in, traps some heat, moves energy through winds, forms clouds, and creates weather systems that distribute warmth around the planet. Earth's oceans are even more powerful. They store enormous amounts of heat. They move it through currents. They prevent temperatures from changing too quickly. They turn our planet into something stable enough for life. Take away the atmosphere and oceans, and Earth would become far more extreme. Days would burn, nights would freeze, shadows would become harsher. Life, as we know it, would struggle or vanish. This is why the moon feels like a warning. It shows what sunlight and darkness become when there is almost nothing between a surface and space. The moon is not cold everywhere. It is not hot everywhere. It is divided by exposure. Where light touches, energy arrives. Where light cannot reach, the universe takes over. And the universe, left alone, is cold. This same principle shapes spacecraft. A spacecraft moving through sunlight is never heated evenly. Surfaces facing the sun absorb energy. Surfaces facing deep space radiate energy away. Internal systems produce heat. Insulation slows heat loss. Radiators release heat. Rotating the spacecraft can spread sunlight more evenly, but rotation itself must be controlled carefully. Thermal design becomes a kind of choreography. Engineers must decide which surfaces face the sun, which components need shade, which parts need heaters, and which systems must never freeze. Even the color and texture of a spacecraft surface can matter. A dark surface absorbs more sunlight. A reflective surface sends more away. A radiator must release heat efficiently. A delicate instrument may need shielding from direct radiation. Spacecraft are painted, wrapped, angled, and controlled with thermal survival in mind. This is not only engineering, it is adaptation. In space, machines must behave almost like living things. They must regulate themselves. They must maintain internal conditions, despite a hostile exterior. They must keep their fragile parts within survivable limits. A human body does the same thing. We maintain internal temperature through metabolism, blood flow, sweating, shivering, clothing, shelter, and behavior. We are warm-blooded creatures because our biology constantly produces and manages heat. But a spacecraft has no biology. It uses electronics, pumps, insulation, sensors, heaters, and radiators to imitate what life does naturally. And if those systems fail, cold enters the story quickly. Not as a visible creature, not as a cloud, not as frost instantly racing across every wall, but as a slow shift in numbers, a battery temperature dropping, a pipe approaching its freezing point, a sensor falling outside calibration, a joint stiffening, a lubricant thickening, a circuit board becoming unreliable. Cold can turn technology against itself. A spacecraft that was powerful near Earth can become vulnerable in deep shadow or far from the sun. A lander that survives touchdown can still die during a long night. A rover that explores bravely during daylight can freeze when darkness falls. An instrument that works for years can fail if heating power declines. This is why planetary nights are so important. A night on Earth lasts hours. A night on the Moon lasts about 2 weeks. For a lunar lander, surviving that night is difficult. Without sunlight, solar power stops, temperatures plunge, batteries drain. Heaters must keep critical components alive. If power runs out, the machine may never wake again. Think about that. A robot built by human hands, launched across space, landed on another world, still full of potential, still physically present, but silent forever because the night was too cold. That is the kind of ending space often gives. Not dramatic destruction, just stillness. Mars has its own version of this. Mars is farther from the sun than Earth, and has a thin atmosphere that cannot hold heat well. Its surface can experience great temperature swings. Rovers and landers must survive cold nights, dust, seasonal changes, and reduced sunlight. Some missions have ended because of power loss, dust-covered solar panels, or thermal challenges. Even when a machine is not physically broken, it can be defeated by the loss of energy needed to stay warm. In space exploration, power is warmth, and warmth is life. This becomes even clearer when we look at the outer planets. Far from the Sun, solar energy fades. A spacecraft near Jupiter receives far less sunlight than it would near Earth. At Saturn, even less. At Uranus and Neptune, sunlight becomes pale and weak. Solar panels must become enormous or impractical. Many missions rely on nuclear power, not for dramatic thrust, but for steady electricity and heat. That heat is precious. A small amount of controlled warmth can keep electronics alive in a region where sunlight is too weak to help. The idea is almost poetic. Humanity sends machines into darkness, carrying tiny artificial sources of warmth, like embers from Earth. They move past planets, moons, rings, and ice, surviving because they can hold back the cold just enough to keep thinking, measuring, transmitting, and remembering. Voyager is one of the most powerful examples. Launched in the 1970s, the Voyager spacecraft traveled far beyond the giant planets and into interstellar space. They are now incredibly distant from Earth, where sunlight is weak and communication takes many hours. Their power slowly declines over time as their nuclear sources produce less electricity. One by one, systems must be managed carefully. Instruments are turned off. Power is conserved. Heat becomes limited. The spacecraft continues, but only because engineers stretch its life with extraordinary care. A spacecraft that far away feels almost alive in our imagination. Not alive like an organism, a small human-made object moving through deep cold, carrying a record of Earth, drifting beyond the influence of the planets, still connected to us by signals weaker than a whisper. And eventually, even Voyager will fall silent, not because it reaches a wall, not because space ends, but because the energy that keeps it communicating will fade. The cold will remain. The spacecraft will continue moving, but its voice will be gone. That is one of the most haunting truths about space. Motion can continue after life, after power, after purpose. An object can drift for millions or billions of years, frozen, silent, and unreachable, carrying the shape of human effort through a universe that does not notice. Cold makes that future feel inevitable. When power ends, activity ends. When activity ends, temperature falls. When temperature falls, the machine becomes part of the stillness. This is not only true for spacecraft, it is true for worlds. A planet without enough heat can become geologically quiet. Its atmosphere may freeze, escape, or thin away. Its surface may preserve old impacts. Its chemistry may slow. Its oceans, if exposed, may turn to ice. Its potential for life may retreat underground or vanish. Cold can silence a planet. But sometimes, cold also protects secrets. This is why icy moons remain so fascinating. Europa, Enceladus, Titan, Triton, and other distant bodies may appear frozen and hostile, yet they may preserve complex chemistry, hidden oceans, or ancient materials beneath their surfaces. The surface says death. The interior may say, wait. On Europa, tidal forces from Jupiter may flex the moon, generating internal heat. Beneath the ice, a global ocean may exist. On Enceladus, geyser-like plumes suggest material escaping from a subsurface ocean. Titan's cold atmosphere and hydrocarbon lakes create chemistry unlike Earth, but deeply interesting for understanding what chemistry can do in low temperatures. These worlds teach us that cold is not simple. Cold can kill, cold can preserve, cold can hide, cold can slow time. Cold can build shells around possible oceans. Cold can turn a world's surface into armor. For life, the question is not only whether a place is cold, the question is whether any warmth survives somewhere. On Earth, warmth is open. It covers the surface, It fills the oceans, it moves through the air, it supports forests, animals, weather, and human civilization. On icy moons, warmth may be buried. It may exist under kilometers of ice, separated from the sun, powered by gravity, chemistry, and internal energy. If life exists there, it may never see a sunrise. That thought is extraordinary. Life may not always need a warm sky. It may need a warm boundary, a place where water, chemistry, and energy meet, even if the surface above is frozen forever. This expands our imagination. When we say space is freezing, we should not imagine only lifeless emptiness. We should imagine a universe where warmth is hidden, fragile, unevenly distributed, and often protected beneath cold surfaces. The cold does not always mean nothing is happening. Sometimes it means something is happening in secret. But for humans, the problem remains. We are surface creatures from a warm planet. We depend on sunlight, air, liquid water, and a narrow biological temperature range. We are not built for buried oceans, frozen plains, or permanent shadows. To reach those places, we must bring Earth with us. Every heater in a rover, every insulated wall in a habitat, every thermal layer in a spacesuit, every nuclear power source in a distant probe, every radiator on a spacecraft. All of these are acts of resistance against the cosmic default. The more we explore, the more we realize that space is not just a place of distance. It is a place of thermal loneliness, a place where warmth must be carried, defended, recycled, and rationed. A place where shadows can last longer than civilizations. A place where machines freeze not because they are weak, but because the universe is patient. And as you listen tonight, warm under a roof, breathing air without thinking, it becomes almost impossible not to feel the difference. Your room may be quiet, but it is not empty. The darkness outside your window may be cool, but it is not cosmic. The night around you may feel still. But morning will come. On the moon, some shadows do not know morning. In deep space, some objects will never be warmed again, and far beyond the comfort of Earth, cold waits not as a season, not as weather, not as a passing night, but as the ancient background of the universe itself. There is another reason space feels so terrifyingly cold. It is not only because the universe lacks warmth, it is because the universe is always trying to take heat away from anything that has it. A planet, a moon, a spacecraft, a human body, a tiny piece of dust drifting between stars. Every warm object in the universe is constantly losing energy. Some lose it quickly, some lose it slowly, some are warmed again by sunlight, radioactivity, friction, chemistry, or life. But without a source feeding warmth back in, heat always leaks away. This is one of the quiet laws behind everything. Warmth does not stay forever by itself. It must be renewed. On Earth, we rarely notice this, because renewal is happening everywhere. The sun rises every day. The atmosphere traps some heat. Oceans store warmth. Winds move it around. Fires burn. Bodies produce heat. Cities glow. Machines run. Homes are heated. Food becomes energy inside us. Earth feels alive because energy keeps flowing. But space reveals what happens when that flow becomes weak. A rock floating far from the sun does not have a blanket of air around it. It does not have clouds holding warmth close. It does not have oceans releasing stored heat through the night. If it has no internal heat, it slowly radiates what warmth it has into the darkness, and the darkness does not return it. This is why the cold of space feels so absolute. It is not a storm attacking from one direction. It is not winter arriving for a few months. It is a background condition surrounding everything, waiting patiently for energy to fade. The universe does not need to freeze something instantly. It can simply wait. This waiting is what makes deep space so haunting. Imagine a spacecraft traveling farther from the sun. At first, the ship is alive with energy. Lights glow inside the cabin. Computers hum. Pumps circulate fluids. Heaters protect fuel lines. Radiators release excess heat. Batteries charge and discharge. The crew moves through the spacecraft, breathing warm air inside a carefully controlled environment. From the inside, it may feel safe, but outside, the spacecraft is surrounded by an endless cold emptiness that would become deadly the moment the systems stopped working. The warmth inside is not natural. It is being created every second. That means survival is not a state. Survival is an activity. The spacecraft must continue fighting. It must continue managing heat. It must continue generating power. It must continue moving warmth from one place to another. It must keep the crew's environment within a narrow range, even while the universe outside offers nothing. If the power fails, the spacecraft does not become cold in a dramatic cinematic instant. Instead, the temperature begins to drift. At first, perhaps nothing seems different. The walls still feel familiar. The air still carries some stored warmth. Machines retain heat from earlier operation. People still breathe, but slowly the numbers fall. One compartment becomes colder than expected. A pipe approaches a dangerous temperature. Condensation begins forming where it should not. A battery loses efficiency. A valve becomes harder to move. A screen flickers. A backup heater activates. Then, another. The crew may not see the cold directly. They see it through warnings. Cold in space often appears first as data. A decreasing temperature reading. A system outside safe range. A power budget shrinking. A thermal map turning dangerous. This is the strange horror of spacecraft life. The environment can remain quiet while danger grows. No wind enters. No frost-covered storm hits the windows. No sound comes from outside. Only numbers changing. And behind those numbers is the universe reclaiming heat. For astronauts, this would be one of the deepest psychological challenges. On Earth, when a room becomes cold, we understand it. We can feel where the draft comes from. We can close a window. We can add clothes. We can move to a warmer place. We can light a fire or turn on heating. But in space, cold is not solved by moving somewhere else. There is no outside shelter. The entire spacecraft is the shelter. And if the shelter itself begins to lose the ability to stay warm, there is no larger world waiting beyond it. This is why spacecraft design is built around redundancy. Engineers do not trust one system when human life is at stake. There are backups, emergency modes, alternate circuits, insulated zones, heaters for critical components, careful routing of fluids, and procedures for thermal survival. But redundancy has limits. A spacecraft cannot carry infinite spare parts. It cannot carry infinite energy. It cannot prepare for every possible failure across years of travel. The longer the mission, the more the cold becomes a slow test of endurance. Not only for the astronauts, but for the materials themselves. Every material has a story under temperature. Metal expands when heated and contracts when cooled. Rubber and seals can become less flexible. Plastics can become brittle. Lubricants can behave differently. Batteries can lose power. Electronics can drift outside their expected performance. Sensors can become unreliable. Mechanisms that moved smoothly on Earth may stiffen in the cold. A machine is not simply a machine in space. It is a machine under thermal stress. Repeated cycles of heating and cooling can fatigue materials over time. A surface that faces sunlight may heat strongly, then cool sharply in shadow. This expansion and contraction can create stress, especially over months and years. Spacecraft are designed for this, but design is always a battle against reality. Because reality has time, a mission lasting days can survive with one kind of protection. A mission lasting months needs more. A mission lasting years becomes something else entirely. And a mission lasting decades enters the realm of patience, where every tiny weakness may eventually reveal itself. Cold is patient. This patience can be seen across the solar system. Look at comets drifting far from the sun. For most of their existence, they are frozen bodies moving through darkness. Their ices remain locked away in deep cold. But when a comet approaches the sun, warmth awakens it. Frozen materials begin to vaporize, gas and dust escape. A glowing coma forms. A tail stretches across space. For a brief time, The comet becomes dramatic. Then it moves away again. The sun weakens. Activity fades. The comet returns to cold silence. A little heat can transform a frozen object into something glowing and active. Remove the heat, and the same object becomes still again. Warmth creates motion. Cold preserves stillness. The same idea appears on icy moons, dwarf planets, and frozen bodies at the edge of the solar system. When sunlight is weak and internal heat is limited, surfaces change slowly. Ice becomes hard. Chemistry quiets. Ancient scars remain visible. Time seems to stretch. On Earth, landscapes change constantly. Rain erodes stone. Rivers cut valleys. Plants break rock apart. Ice melts and refreezes. Winds reshape deserts. Oceans swallow coastlines. Volcanoes create new land. Life covers almost everything. Earth is restless because it is warm. A frozen world is different. It can hold the past for staggering lengths of time. This is why cold is connected to memory in space. A warm planet like Earth is beautiful, but it does not preserve everything. It changes too much. Its surface is recycled, weathered, buried, melted, reshaped, and alive. Cold worlds are quieter archives. They may keep records of the early solar system in ice and cratered surfaces. They may preserve materials that were present when planets were forming. They may carry frozen chemistry from ancient impacts, ancient dust, ancient sunlight. To scientists, cold is not only an obstacle. It is a librarian. It stores what warmth would erase. But for humans, the same preservation becomes terrifying because it reminds us how temporary warmth really is. If a spacecraft were abandoned in deep space, it would not decay the way a vehicle decays on Earth. There would be no rain to rust it in the familiar way, no oxygen-rich atmosphere to weather it quickly, no plants to grow over it, no soil to bury it through ordinary seasons. It might drift for enormous periods of time, slowly battered by radiation, micrometeoroids, and thermal changes, but still recognizable far longer than anything left outside on Earth. Cold and vacuum can preserve objects in strange ways. A dead spacecraft could become a fossil of technology, a silent shape moving through darkness long after the civilization that built it has changed beyond recognition. This is one of the reasons space feels so emotionally powerful. It does not always destroy by breaking things apart quickly. Sometimes it preserves them after removing their life, their warmth, and their purpose. A probe stops transmitting. A lander freezes. A rover falls silent. A spacecraft loses power. The object remains. And in space, voice matters. Every signal from a distant spacecraft is proof that warmth and electricity still exist somewhere inside it. A tiny transmission crossing millions or billions of kilometers tells us that a machine built on Earth is still awake. When those signals stop, the silence feels almost personal. The spacecraft may still be there, but we no longer hear it. It has joined the cold background. This same idea applies to human exploration in a more emotional way. A future habitat on the Moon or Mars would not simply be a building. It would be a thermal promise. Inside, people would breathe, sleep, work, eat, and dream because warmth was being maintained. Outside, the environment would remain hostile. On the Moon, the long night would press cold against the habitat. On Mars, the thin atmosphere and freezing temperatures would challenge every system. In the outer solar system, habitats would need powerful energy sources just to keep humans alive. A space habitat is not like a house in a harsh climate. A house on Earth is still surrounded by a living planet. If heating fails, conditions may become dangerous, but there is air outside. There may be neighbors, roads, emergency help, wood, fire, shelters, sunlight, and weather that eventually changes. A habitat beyond Earth cannot depend on those things. Its warmth is manufactured. Its air is manufactured. That makes it incredibly precious. A warm room on Mars would be one of the most fragile places in the solar system. Behind a wall, humans could laugh, read, cook, repair equipment, study samples, speak to Earth, or sleep. A few meters away, outside that wall, the environment would not support an unprotected human body. The difference would be engineering, nothing more. This is humbling, because it shows that human life in space would not be a conquest of the cold. It would be a negotiation with it. We would never defeat the cold of the universe completely. We would create small warm volumes within it. Cabins, suits, stations, habitats, tunnels, greenhouses, ships. Little islands of controlled temperature. And every island would need power. This is why energy becomes sacred in space. Power is not just electricity. Power is heat. Power is communication. Power is water recycling. Power is oxygen generation. Power is food growth. Power is medicine storage. Power is computer guidance. Power is the difference between a living habitat and a frozen shell. On Earth, losing power is inconvenient and sometimes dangerous. In deep space, losing power can threaten every layer of survival. The cold is always outside the system, waiting for the energy flow to stop. This makes the sun even more important. Near Earth, sunlight feels endless, but it is not evenly useful everywhere. It comes from one direction. It can be blocked by shadow. It weakens with distance. Solar panels depend on orientation, cleanliness, and exposure. Dust can reduce them. Long nights can stop them. Far from the sun, they may not provide enough power for human needs. Beyond a certain point, humanity must carry its own reliable energy. Nuclear power may become essential for deep space exploration, not because it is dramatic, but because sunlight fades. A steady power source can keep systems warm through long darkness, support habitats, and allow machines to function where solar energy is too weak. In the outer solar system, a habitat without dependable energy would be like a campfire in an endless frozen desert. Beautiful for a moment, then gone. This is where the cold of space connects to the future of human civilization. If we ever build settlements beyond Earth, the first question will not only be where we can land, it will be where we can keep energy flowing long enough to survive. A settlement is not a flag. It is not a footprint. It is not a photograph. A settlement is a continuous thermal system. It must stay warm through day and night, through dust storms, eclipses, equipment failures, seasonal changes, radiation events, and human mistakes. It must store energy, distribute heat, protect water, grow food, and keep living spaces safe. Every colony would be a struggle against entropy. Entropy is the tendency of energy to spread out, of order to become disorder, of warmth to disperse into cold surroundings unless work is done to maintain it. On Earth, life fights entropy constantly. Cells repair themselves, bodies regulate temperature, ecosystems cycle energy, civilization builds shelters and machines. In space, that fight becomes visible. A warm habitat against a frozen landscape is entropy made dramatic. Inside, order. Outside, stillness. Inside, breath. Outside, vacuum or thin alien air. Inside, light. Outside, darkness. Outside, cosmic time. This contrast may define the emotional experience of future explorers. They will understand, more deeply than anyone before them, that warmth is not guaranteed. Every meal, every breath, every sleeping room, every growing plant, every cup of liquid water will depend on systems that must not fail. A greenhouse on Mars might become more meaningful than a cathedral. Rows of plants under artificial light, leaves opening in a controlled atmosphere, water moving through tubes, warmth held carefully beneath protective panels. This would not just be agriculture. It would be proof that Earth's living processes can be carried into a cold world. And yet even the greenhouse would be surrounded by danger. A cracked window, a failed pump, a loss of heat, a power shortage. The cold outside would not need to enter violently. It would only need access. This is why space architecture will be different from architecture on Earth. Buildings will not be designed only for beauty, comfort, or efficiency. They will be designed as life support organisms. Walls will be shields. Floors will carry thermal lines. Windows may be rare or heavily protected. Underground habitats may offer better temperature stability. Airlocks will become thresholds between life and death. Heat recycling will be as important as decoration. Human culture may change around this. On Earth, we often waste heat without thinking. Buildings leak warmth, engines release waste heat, cities glow at night. We live inside a world where energy is abundant enough to be careless. In space, waste becomes dangerous. Heat must be captured when useful and released when harmful. Water must be recovered. Air must be cleaned. Materials must be reused. The cold teaches discipline. A civilization raised in space would think differently. It would understand that comfort is built from precision. It would know that every warm room has a cost. It would respect maintenance, because maintenance is survival. It would see energy not as an invisible utility, but as the heartbeat of the habitat. And perhaps that is one of the lessons space cold can teach people on Earth. Our planet is also a habitat, a natural one. It has thermal systems, energy flows, atmospheric balance, ocean seasons, and cycles that keep life alive. We did not build them, but we depend on them completely. Space makes this visible by removing them. When you imagine a spacecraft struggling to stay warm, you begin to understand that Earth is doing something similar on a planetary scale. It holds warmth, moves energy, protects water, shields life, and keeps the surface within a narrow range where biology can continue. Earth is not just where we live. It is the most advanced life support system we know. The cold beyond it helps us see that, not through comfort, but through contrast, because beyond the atmosphere, warmth must be defended by machines. Here, warmth is given by a world. That does not make it infinite. It makes it precious. The terrifying truth about space cold is not only that deep space is freezing, it is that everything warm is temporary, unless something protects it. Stars burn fuel. Planets lose heat. Machines run out of power. Bodies cool when life ends. Habitats fail if they are not maintained. Warmth is always a process, never a permanent possession, and this gives the universe a strange sadness. Every star in the sky is a temporary fire. Every planet is holding or losing heat. Every moon is preserving a different story of sunlight and shadow. Every spacecraft is a small attempt to carry order through a place that does not care if it fades. Yet, this sadness is also beautiful, because life exists anyway. Against the cold, Earth became warm. Against the darkness, stars formed. Against stillness, chemistry moved. Against emptiness, consciousness appeared. Against the vacuum, humans built spacecraft. Every act of exploration is an act of warmth leaving home. A probe powered by fading energy. A rover surviving one more night. An astronaut protected by a suit. A habitat glowing under alien stars. A signal crossing the dark. Small warmths, temporary warmths, but real. And maybe that is why space feels so powerful to us. It shows us how fragile warmth is, but also how meaningful it becomes. Because it is fragile, a warm room on Earth may seem ordinary. A warm cabin in deep space would feel like a miracle. A breath here may seem automatic. A breath on Mars would be engineering, courage, and trust. A sunrise here may pass unnoticed. A sunrise after a lunar night could mean survival. The cold of space changes the value of everything. It makes warmth sacred. It makes shelter sacred. Tonight, as the thought of deep space surrounds this story, there is one image worth holding in your mind. A spacecraft moving silently beyond the moon, beyond Mars, beyond the familiar blue of Earth. Around it, the universe is black and cold. Behind it, the sun shines smaller than before. Inside it, a few lights glow. Warm air moves gently through the cabin. A human hand touches a wall that is warm enough to feel safe. Outside that wall, there is cosmic cold. Inside, there is life. And the difference between them is everything. There is a strange comfort in looking at stars from Earth. They seemed peaceful. They glitter above sleeping cities, above deserts, above oceans, above mountains, above every human life that has ever looked upward and wondered what lies beyond. From the ground, stars feel gentle. They feel distant enough to be beautiful, but not close enough to threaten us. But the stars are not gentle. They are furnaces. They are vast nuclear fires burning in the dark, releasing energy powerful enough to shape planets, destroy atmospheres, melt ice, drive storms, and decide whether worlds can live or freeze. Every warm planet depends on a star. Every frozen world tells a story about being too far away, too poorly protected, or too unlucky to keep enough warmth. And Earth survives because it sits in a rare relationship with the Sun. Not too close, not too far, not too exposed, not too sealed away. We live inside a narrow band of possibility. This band is often called the habitable zone, the region around a star where a rocky planet could, under the right conditions, support liquid water on its surface. But that phrase can sound too simple. It makes it seem as if life is just a matter of standing at the right distance from a star. The truth is more delicate. A planet can sit in the habitable zone and still be dead. A planet can receive sunlight and still freeze. A planet can be warmed by a star and still lose its atmosphere. A planet can have heat and still become hostile to life. Warmth alone is not enough. It must be the right kind of warmth, held by the right atmosphere, balanced by the right chemistry, stabilized over immense periods of time. Earth did not become alive simply because the sun existed. It became alive because energy arrived in a way life could use. Sunlight reaches Earth, passes through the atmosphere, warms the surface, powers plants, drives weather, moves oceans, and feeds nearly every ecosystem we know. The sun's energy becomes leaves, food, oxygen, wind, waves, rain, forests, animals, and eventually human thought. The warmth around you right now began as light from a star. That is almost impossible to feel in daily life. When you sit in a room, wrapped in a blanket, hearing quiet sounds around you, you do not usually imagine nuclear fusion at the heart of the sun. You do not imagine photons traveling across space for about 8 minutes before touching Earth. You do not imagine ancient sunlight stored in plants, food, wood, coal, oil, weather, and life. But warmth is cosmic. Every comfortable moment on Earth is connected to a star. And this is what makes space cold so terrifying. Away from stars, warmth fades. Away from stars, chemistry slows. Away from stars, worlds become dark, frozen, and quiet, unless they carry some hidden internal energy of their own. The sun is not just a bright object in our sky. It is the reason Earth is not another frozen stone. But the sun's protection is limited. It does not fill the entire universe with comfort. Its warmth weakens with distance. Move twice as far away, and sunlight becomes much weaker. Move 10 times farther, and the sun becomes only a pale provider compared with what Earth receives. This is why the solar system changes so dramatically as we move outward. Near the sun, heat dominates. Farther out, ice begins to rule. Beyond Mars, frozen materials become more common. Beyond Jupiter and Saturn, the solar system becomes a realm of icy moons, faint sunlight, and worlds that would be impossible for humans to survive on without machines. Distance turns the same star into a different experience. From Earth, the sun is life. From Mars, it is weaker but still central. From Jupiter's moons, it is far less powerful. From Neptune, it is a bright point in a cold sky. From the outer edge of the solar system, it becomes one star among many, special only because it is ours. That gradual weakening changes everything. Imagine traveling outward from Earth in a spacecraft. At first, sunlight still feels familiar through instruments and windows. The sun remains large enough to dominate orientation. Earth is still close enough to feel emotionally real. But as the journey continues, the ship enters a colder relationship with the star that made humanity possible. The sun shrinks. Its warmth becomes less generous. The spacecraft must rely more heavily on stored energy, nuclear power, insulation, and carefully controlled systems. The crew can no longer think of sunlight as an endless background source. Every watt matters, every heater matters, every thermal decision matters. The farther you travel, the more you understand that warmth is not spread evenly through creation. It is concentrated near fires, and stars are the fires. Yet even stars are temporary. This is the deeper truth. The sun feels eternal because human lives are short. Every generation has seen it rise. Every civilization has depended on it. It watched over the first humans, the first farms, the first cities, the first ships, the first telescopes, the first rockets, and every dream of space travel. But the sun is not eternal. It is burning fuel, very slowly by human standards, but not forever. Billions of years from now, it will change. It will grow brighter, larger, and more unstable. Earth's oceans will not remain safe forever. The gentle balance that allows life today will eventually fail. This means even Earth's warmth has an expiration date. Not soon, not tomorrow, not in any time close to human history. But in the deep future, the world that feels so stable beneath us will be transformed by the same star that once protected it. The sun gives life. One day, it will take it away. That is the unsettling relationship every planet has with its star. Too little energy and a world freezes. Too much energy and a world burns. A star changes and the planet's fate changes with it. Life exists inside a moving balance. For a while, Earth sits in the right place. For a while, oceans remain liquid. For a while, the atmosphere holds enough warmth. For a while, seasons remain survivable. For a while, biology flourishes. But space teaches us that, for a while, can be the most important phrase in the universe. Everything warm exists for a while, stars burn for a while, planets remain stable for a while, civilizations rise for a while, human bodies remain warm for a while. The cold is older than all of it, and it waits beyond the edges. This does not make life meaningless. It makes life rare. It makes every warm world precious. Astronomers search for planets around other stars, not only because we want to know what is out there, but because we want to know how common warmth really is. We want to know whether Earth is one example among countless living worlds, or something much more fragile and unusual. Thousands of exoplanets have been discovered. Some are giant gas worlds orbiting close to their stars. Some are scorched rocky planets. Some are frozen worlds far from warmth. Some orbit red dwarf stars, small and dim, where the habitable zone lies much closer to the star. Some may be ocean worlds. Some may be wrapped in thick atmospheres. Some may be barren stones. Each one asks the same quiet question. Can warmth become life there? But habitability is complicated. A planet too close to its star may be locked in a permanent day and night, one side facing the star, the other side turned toward darkness. The day side may bake, while the night side freezes. If it has the right atmosphere, heat might circulate. If it does not, the world may become divided between fire and ice. A planet around an active red dwarf may receive enough warmth but also face powerful stellar flares that strip atmospheres or bathe the surface in harmful radiation. A planet farther out might freeze unless greenhouse gases trap enough heat. A planet with too much greenhouse effect might become like Venus, where heat is trapped so intensely that the surface becomes crushing and hostile. Again and again, the universe shows that temperature is not only about distance, it is about balance. And balance is difficult. Earth's atmosphere is not too thin and not too thick. Its oceans are not completely frozen and not boiled away. Its rotation creates day and night. Its magnetic field helps shield the planet. Its geology cycles carbon over long periods. Its moon stabilizes some aspects of its axial tilt. Its life forms have altered the atmosphere itself. Earth is not just located well. Earth is coordinated. A living symphony of physical systems, chemical cycles, and cosmic timing. This is why calling space freezing does not only mean that deep space has low temperature, it means the universe is mostly not balanced for life. Most places do not have the right energy flow. Most places do not hold warmth gently. Most places are either too exposed, too empty, too cold, too hot, too unstable, or too far from steady energy. Life does not arise in the average condition of the universe. Life arises in rare pockets where conditions resist the average. The average is darkness. The average is thinness. The average is cold. Earth is not average. Earth is a warm exception with oceans. That may be the most humbling truth in astronomy. When we look for life beyond Earth, we are looking for other exceptions, other places where cold did not win completely, other places where warmth remained long enough for chemistry to become biology, other places where energy flowed without destroying everything it touched. And maybe they exist. Maybe the galaxy is full of small, warm worlds orbiting distant stars, each with its own clouds, oceans, mountains, storms, and living things. Maybe some are nothing like Earth. Maybe some are hidden beneath ice. Maybe some exist in deep oceans inside frozen moons. Maybe some orbit dim stars under red skies. But even if life is common, warmth would still be precious. Every living world would be a candle in a vast dark hall. Each one would need protection. Each one would need energy. Each one would depend on a balance that could change. Stars evolve. Orbits shift. Atmospheres escape. Impacts occur. Ice ages come and go. Volcanoes awaken and die. Climate changes. Magnetic fields weaken. Moons drift. Planets age. No warm world is guaranteed forever. This gives the cold of space a deeper meaning. It is not only a danger outside spacecraft, it is the background against which all life struggles to remain active. Life is warm movement against cosmic stillness. A seed growing from soil, a fish moving through water, a forest breathing with sunlight, a human heart beating in the dark, a spacecraft cabin glowing beyond the moon, a future habitat keeping plants alive under artificial lamps. All of it is resistance. Not violent resistance, not loud resistance, but steady, fragile resistance against the natural spread of energy into emptiness. The story of life may be the story of keeping warmth organized for as long as possible. This is why temperature shapes destiny. On a world too cold, water freezes and chemistry slows. On a world too hot, complex molecules break down and oceans vanish. On a world with no atmosphere, heat escapes too quickly. On a world with too much atmosphere, heat becomes trapped dangerously. On a world with no energy source, everything falls quiet. On a world with unstable energy, life may never get enough time. The universe does not need to prevent life intentionally. It only needs to be difficult. And it is difficult almost everywhere. This is what makes Earth feel almost sacred after thinking about space cold. Not sacred in a distant or abstract way, sacred in the sense that every ordinary detail becomes meaningful. A warm breeze, a cup of tea, a morning window, a soft bed, a beach under sunlight, a tree casting shade, rain falling from clouds, a city glowing at night, a hand touching another hand, and feeling warmth. These are not small things. They are the visible signs of a planet that has not frozen, not burned, not lost its air, not drifted into darkness, not become still. They are signs of a world where energy is still flowing through life. And when we imagine astronauts looking back at Earth from space, perhaps this is part of what they feel. They are not only seeing a beautiful planet, they are seeing the rare warmth of home surrounded by blackness, a blue world wrapped in thin air, a soft sphere in a hard universe, a place where cold did not rule completely. From orbit, the atmosphere looks impossibly thin, just a delicate glow around the planet. And yet that thin glow helps separate everything we know from the vacuum outside. Below it, oceans move, clouds form, cities shine, animals sleep, people dream, plants turn sunlight into breath. Above it, the universe waits, silent, open. Cold, this contrast is almost too powerful to hold in the mind. The same space that appears beautiful from the ground becomes terrifying when we understand what it lacks. It lacks pressure. It lacks air. It lacks warmth. It lacks mercy. It lacks the gentle mixing that makes Earth habitable. And still, we are drawn to it. Perhaps because humans are creatures of warmth, who long to understand the cold. We want to know what lies beyond the sky. We want to send machines into the darkness. We want to walk on worlds where no human body could survive unprotected. We want to find other warm places. We want to know whether the universe is mostly empty or secretly alive. That desire is one of the most extraordinary things about us. A species born on a warm planet has learned enough to measure the cold between stars. But knowledge brings responsibility. The more we understand space, the more we understand Earth's fragility. The more we study frozen moons, dead planets, and airless rocks, the more we see that habitability is not guaranteed. The more we explore, the more valuable our own world becomes. Space exploration should not make Earth feel small in a careless way. It should make Earth feel rare. Small, yes, but rare, fragile, alive, a warm exception in the dark. And maybe that is the emotional center of this entire journey. Space is freezing, not just because the temperature is low, but because warmth is not the rule. Warmth is something stars create, planets hold, atmospheres protect, oceans distribute, bodies produce, and technology defends. Warmth is effort. Warmth is balance. Warmth is time borrowed from the cold. Far from stars, cold dominates. In shadows, cold gathers. On dead worlds, cold preserves silence. Around fading machines, cold waits for power to end. At the edge of the solar system, cold stretches across distances too large for the human heart to understand. But here, tonight, you are warm. That fact is more cosmic than it seems. You are warm because a star burns at the right distance, because Earth holds an atmosphere, because oceans have not frozen, because generations learn to build shelters, weave blankets, light fires, generate power, grow food, and survive winters, because your body is still turning energy into life. You are a tiny warm event in a vast cold universe, and that is not something to fear only. It is something to feel deeply, because once we understand how cold space really is, warmth becomes more than comfort. It becomes wonder. The sun becomes more than daylight. Earth becomes more than ground. A room becomes more than shelter. A breath becomes more than habit. Everything warm becomes a miracle continuing for one more moment. And beyond the atmosphere, beyond the moon, beyond Mars, beyond the frozen moons and distant planets, the cold waits as it has always waited. Patient, silent, immense. But for now, Earth glows. For now, the oceans move. For now, clouds carry sunlight and shadow across the world. For now, hearts beat in warm bodies beneath a protective sky. And somewhere in that quiet truth is the most beautiful answer to the terror of cold space. The universe may be freezing, but here, for a little while, there is warmth. There is a point where cold stops being only an environment and becomes a test of endurance. A spacecraft can be designed for it. A spacesuit can resist it. A rover can survive it for a while. A habitat can fight against it with power, insulation, and careful engineering. But the farther we travel from Earth, the more every form of warmth becomes a question. How long can it last? That question follows every machine humanity sends into space. It follows every lander sitting on a frozen surface, every probe crossing the darkness, every imagined human base beneath alien skies. It follows every future astronaut who may one day walk on Mars, work near the moons of Jupiter, or live inside a habitat where the sun is no longer strong enough to feel like home. In the beginning, warmth seems controllable. You bring heaters, you bring fuel, you bring power systems, you wrap the spacecraft in insulation, you build backup circuits and thermal sensors, you test the machines in vacuum chambers on Earth. You try to prepare for the cold before the cold ever touches the mission. But space has time, and time changes everything. A spacecraft may function perfectly on day one. It may survive launch, orbit insertion, course corrections, and months of travel. Its systems may remain stable, Its temperature may stay within safe margins. Its power may flow exactly as expected. Then slowly the mission ages. A heater becomes less efficient. A battery no longer holds the same charge. Dust covers a solar panel. A cable degrades. A thermal coating darkens after years of radiation. A valve begins responding more slowly. A sensor gives numbers that must be checked twice. Nothing dramatic has happened. But the spacecraft is not as young as it was. This is one of the hidden dangers of cold space. The cold itself may not always destroy a mission immediately. Instead, it becomes part of a long pressure on everything that must keep working. Every system is asked the same question again and again. Can you survive one more cycle? One more night? One more shadow? One more orbit? One more winter? On Earth, machines can be serviced regularly. Parts can be replaced. Technicians can walk up with tools. Worn pieces can be removed. New ones can be installed. If a car fails in winter, it can be brought into a garage. If a house loses heat, someone can repair the furnace. If a battery dies, another can be purchased. In space, maintenance becomes a battle against distance. A rover on Mars cannot be brought home for repairs. A probe near Saturn cannot receive new parts. A spacecraft beyond the planets cannot wait for a mechanic. Whatever it carries is all it has. This makes cold feel different from a storm. A storm passes. Cold in deep space does not pass. It is always there, surrounding the mission, touching every exposed surface through radiation balance, waiting for weakness. A spacecraft is not only exploring a destination, it is slowly spending its own survival. Power is spent. Materials are spent. Redundancy is spent. Heat is spent. The mission continues as long as enough of that survival remains. This is why long-duration exploration is one of the most difficult dreams humanity has ever had. Reaching a place is hard, but staying alive there is harder. Landing on a cold world is impressive, but surviving the night can be the true test. Think of the moon. It is close to Earth, familiar in the sky, and only days away by spacecraft. Yet the lunar night is harsh enough to challenge machines built with modern engineering. For about 2 Earth weeks, a location on the moon can remain in darkness. No sunlight reaches solar panels. Temperatures fall. Electronics and batteries must be protected. A mission may land successfully. It may deploy instruments. It may send back beautiful images. It may roll across the surface and prove that human engineering has touched another world. Then night arrives. The sun disappears behind the horizon. Shadows stretch and merge. The surface begins to lose heat. The lander or rover must depend on stored energy and heaters. During that long darkness, the machine becomes quiet. It waits. And waiting on the moon is not like waiting on Earth. There is no soft dawn a few hours later. There is no atmosphere holding warmth through the night. There is no wind carrying heat from somewhere else. There is no cloud cover, trapping infrared radiation above the ground. The machine sits in cold silence. If it survives, it may wake when sunlight returns. If it does not, it becomes another still object on a still world. That is the fragility of exploration. Sometimes the difference between a working spacecraft and a silent relic is one night. Mars is different, but not gentle. Mars has an atmosphere, but it is thin and dry. It cannot protect warmth the way Earth's atmosphere does. During the day, sunlight can warm the surface. At night, heat escapes quickly. Temperatures can drop far below what humans could survive without protection. Rovers on Mars are not just driving through dust and rock. They are managing energy every day. They must plan movement, science work, communication, heating, and rest. They must consider seasons. They must survive dust storms that reduce sunlight. They must protect batteries from cold. They must keep delicate instruments within operating range. A rover may fail not because it falls into a crater or hits a rock, but because it loses the energy needed to stay warm. That kind of ending feels quiet, but it is deeply powerful. A machine can be perfectly placed on another planet and still be defeated by the slow loss of heat. For future humans on Mars, this lesson will become even more serious. A Martian habitat would need continuous heating. It would need to protect water from freezing, maintain air temperature, keep food production systems alive, and shelter people through dust storms and cold nights. It would likely need to use buried structures, thick insulation, nuclear power, heat recycling, and carefully controlled airflow. A single room on Mars would be a triumph, not because it is large, not because it is beautiful, but because it is warm. A warm room on a cold planet means that civilization has created a small pocket of Earth where Earth does not naturally exist. Inside that room, a person could remove a helmet. They could breathe. They could speak normally. They could sleep. They could hold warm food. They could touch another human hand without a spacesuit between them. Outside, the planet would remain hostile. That contrast would shape the psychology of every settler. On Earth, warmth is so common that we forget it. On Mars, warmth would be planned, measured, and protected. People would know the temperature of their habitat not as background information, but as part of life itself. Children raised there might grow up understanding things that Earth children rarely think about. That air has to be made safe. That water must be guarded. That heat must be produced. That walls are not only shelter, but survival. That outside is not outside in the Earth sense. Outside is a different reality. Cold would not be seasonal. It would be part of culture. And beyond Mars, the cold becomes more alien. In the outer solar system, sunlight is weaker and the distances are greater. Human missions there would need power sources far stronger and more reliable than ordinary solar energy. Habitats near Jupiter or Saturn would face not only cold, but radiation, long communication delays, and difficult orbital environments. A human outpost near an icy moon would be one of the most extreme structures ever imagined. Picture a base buried beneath layers of ice or regolith, with thick shielding against radiation, powerful reactors humming in protected chambers, heat pipes running through the walls, greenhouses glowing under artificial light, and airlocks opening onto a surface where the sun appears small and weak. The people inside would live under constant dependency. Not dependency on Earth alone, but dependency on controlled energy. A failure of heat could become a failure of water. A failure of water could become a failure of food. A failure of food could become a failure of life. Everything connects. Cold does not attack one system. It threatens the chain. This is why future space settlements may be designed almost like organisms. They will need circulatory systems for heat, lungs for air, stomachs for food processing, skin for insulation and shielding, nervous systems for sensors, and immune systems for emergency response. A habitat will need to sense cold before it becomes dangerous. It will need to move heat where it is needed. It will need to store energy for darkness. It will need to isolate damaged sections. It will need to repair itself or guide humans through repair. In deep space, architecture becomes biology. A building must act alive because the environment outside is not. And still, even the best designed habitat will never truly defeat the cold. It will only hold a boundary against it. A wall separates warmth from darkness. A door separates breath from vacuum. A suit separates a body from death. A reactor separates civilization from freezing stillness. The boundary must hold. That may become the deepest emotion of living beyond Earth. Trust in boundaries. On Earth, boundaries are soft. A window separates you from cold air, but if it breaks, the air outside is still breathable. A door separates indoors from outdoors, but beyond it there is still a world where humans can stand. Even in winter, Earth remains Earth. In space, boundaries are absolute. If the ROM wall breaks, the world ends at that wall. This gives cold an almost spiritual weight. It becomes the presence outside the circle of human survival, the thing that cannot be allowed in, the silence beyond the light. Ancient humans gathered around fires in the night. The fire meant warmth, safety, food, story, community, and protection from darkness. Beyond the firelight, the world was unknown. A future space habitat may recreate that ancient feeling in a new form. The reactor becomes the fire. The habitat becomes the cave. The darkness outside becomes deeper than any forest night, and the people inside remain human, gathered around warmth, telling stories while the cold waits beyond the walls. Technology changes. The emotional truth remains. We are creatures who gather around heat. This is why the cold of space connects so strongly to fear and comfort. It reaches into something old inside us. Long before rockets, humans understood that cold could kill. They learned to make fire, wear skins, build shelters, store food, survive winters, and protect children from freezing nights. Civilization itself is partly a history of controlling temperature. Fire changed us. Clothing changed us. Architecture changed us. Agriculture depended on seasons and climate. Cities depended on fuel. Industry depended on energy. Modern life depends on heating, cooling, electricity, and controlled environments. Space exploration is the next chapter of that same struggle. We are still trying to keep warm, only now the night is cosmic, and the fire must travel with us. But there is another side to this story. Cold does not only threaten human survival, it also shapes our search for life beyond Earth. For a long time, people imagined life only on warm surfaces. A planet like Earth, orbiting at the right distance from a star, with liquid water under open skies. That remains one of the strongest possibilities. But icy moons changed the imagination. They showed that a frozen surface may hide a warmer interior. A moon far from the sun may still have liquid water beneath ice, because gravity squeezes and flexes it, creating internal heat. Chemical reactions on the ocean floor may provide energy. Hydrothermal vents may exist in darkness, far from sunlight, like hidden furnaces beneath alien seas. If life exists there, it would be life that never knew warmth from a sky. It would be life protected by cold, not destroyed by it. This is one of the most fascinating contradictions in astronomy. Cold can make a surface deadly, while also preserving the conditions for an ocean beneath. The ice becomes a shield. The darkness becomes protection. The surface becomes a locked door. Some of the most promising places to search for alien life may look frozen and dead from above. Europa, Enceladus, perhaps other icy worlds we have barely explored. Their surfaces are cold enough to destroy unprotected human life quickly. Yet beneath those surfaces, there may be movement, chemistry, and hidden warmth. This teaches humility. The universe may hide its liveliest secrets beneath its coldest faces. But again, for humans, reaching those secrets would be incredibly difficult. Drilling through kilometers of ice on another world, keeping equipment warm, preventing contamination, powering machines far from the sun, and communicating through thick frozen layers would be among the hardest scientific tasks ever attempted. The cold protects the mystery from us. It says, if you want to know what is beneath, you must earn it. Perhaps future missions will send cryobots, robotic probes designed to melt downward through ice. They would carry heat into frozen worlds, slowly descending through darkness, leaving communication lines behind, moving toward hidden oceans that have never seen the sun. That image is almost dreamlike. A warm machine descending through ancient ice on a moon of Jupiter or Saturn, searching for a black ocean beneath, carrying human curiosity into a place older and stranger than any sea on Earth. There may be no life there. Or there may be something small, simple, quiet, and profound. But even the attempt would show what humans are. We are warm creatures sending warmth into cold places to ask whether we are alone. This is the beauty hidden inside the terror. Space is freezing, yes. But the cold does not stop curiosity. It makes curiosity more meaningful. Every mission into cold space is a small rebellion. A spacecraft crosses the dark carrying instruments kept alive by heat. A lander touches a frozen surface and begins to listen. A rover wakes after a night and moves again. A telescope is cooled to extreme temperatures, not because it failed, but because some instruments must be cold to see the universe clearly. This is another surprising truth. Sometimes we use cold. Astronomical instruments can detect faint infrared signals better when they are kept extremely cold, because their own heat would interfere with what they are trying to observe. In that case, cold becomes a tool. A telescope chilled in space can see ancient galaxies, newborn stars, dusty regions, and faint objects that warmer instruments might miss. So cold is not only an enemy, it is also part of how we reveal the universe. It preserves ancient objects. It hides possible oceans. It challenges machines. It protects shadows. It improves certain observations. It marks the natural state of places far from stars. Cold is woven into space science at every level. But for a human body, the meaning remains clear. We are not cold creatures. We are warm life. Our cells depend on liquid water. Our enzymes work in narrow temperature ranges. Our brains need steady blood flow. Our hearts, muscles, and organs depend on internal heat. We can survive cold only by resisting it. When a person lies down under a blanket at night, that blanket is doing a simple version of what spacecraft insulation does. It slows the loss of heat. It traps warmth close to the body. It creates a small protected environment. In a deep way, every blanket is a tiny spacecraft wall. Every heated room is a habitat. Every home is a boundary against a colder outside. The difference is that Earth's outside is still kind compared with space. This thought makes ordinary warmth feel extraordinary. A cup warming your hands, breath that does not freeze, water that stays liquid, skin that feels safe in air, a room that remains comfortable without you thinking about pressure, radiation, or oxygen levels. These things are not ordinary in the universe. They are gifts of a planet still holding its balance. And maybe that is where part 6 brings us. The terrifying truth about how cold space really is does not end with fear. It ends with awareness. Awareness that warmth must be maintained. Awareness that Earth is a rare thermal shelter. Awareness that future explorers will carry tiny worlds into enormous cold. Awareness that machines, habitats, and bodies are all temporary islands of heat. Awareness that even in frozen places, secrets may be waiting under ice. Space is freezing because the universe is mostly without comfort, but that cold makes every warm thing more precious. A star, a planet, a spacecraft cabin, a hidden ocean, a human hand, a sleeping room, a small light glowing in the dark. All of them are fragile refusals to become still. And as humanity looks outward, dreaming of Mars bases, icy moons, distant habitats, and journeys beyond the planets, we are really dreaming of carrying warmth farther than it has ever gone before. Not just heat, life, memory, breath, curiosity, hope, into the cold. Space is freezing, but that is what makes warmth feel sacred. Beyond Earth, there is no gentle air, no safe pressure, no natural shelter, and no promise that heat will remain. The universe is mostly dark, silent, and cold. But here for now, Earth still glows, the sun rises, oceans move, clouds drift, rooms stay warm, bodies breathe. Life continues inside a fragile blue world, protected from the darkness around it. And maybe that is the deepest truth. We do not live in an ordinary place. We live inside a miracle of warmth, surrounded by an endless cosmic cold. Between the planets, cold is already terrifying, but between the stars, it becomes something almost impossible to imagine. There, the sun is no longer a warm presence. It is only one point of light behind you, mixed with thousands of other stars. There are no planets nearby, no moons, no surfaces, no shadows from mountains or craters, no horizon, no sunrise, only distance. Interstellar space is not completely empty, but it is emptier than anything the human mind can easily understand. Tiny particles drift through it. Thin gas stretches across enormous regions. Dust grains float silently in the dark. But compared with the air around you now, it is almost nothing. And in that near nothing, warmth has no place to hide. A spacecraft travelling between stars would become one of the loneliest warm objects imaginable. It would carry heat, electricity, air, water, and human life through an ocean that gives almost nothing back. Every system would matter. The walls would need to hold warmth for years. The power source would need to last longer than any mission before it. The crew would depend on machines not only to move, but to keep the idea of Earth alive inside the ship. Outside, there would be no rescue. No nearby world, no useful sunlight, no place to land if something went wrong. The cold between stars is not dramatic. It does not arrive like a storm. It does not shake the ship. It does not scream against the windows. It simply waits. If power begins to fail, the cabin would slowly lose its warmth. The air would cool. Water systems would become vulnerable. Pipes, electronics, batteries and engines would all enter a quiet fight against the falling temperature. And the most frightening part is that the universe would look unchanged. The stars would still shine. The darkness would still be beautiful. The ship would still drift forward. But inside, every degree would matter. This is why interstellar travel is not only a question of speed, it is a question of warmth. Can a small artificial world stay alive long enough to cross the coldest distances humanity has ever faced? Maybe one day, a future spacecraft will do it. Maybe it will carry people, plants, seeds, memories and machines toward another star. Maybe children born inside that ship will never know natural sunlight the way we do. They may know warmth as something made by reactors, stored in walls, moved through pipes, and protected by alarms. For them, Earth's warmth may sound almost magical. Open air, rain, morning sunlight, a warm ocean, a forest breathing under the sky. Things we call normal may become legends, and that is what the cold of space truly teaches us. Warmth is not just temperature. Warmth is home. Warmth is memory. Warmth is life continuing against a universe that mostly wants stillness. Between the stars, every warm room would be a miracle. Every breath would be engineering. Every light would be resistance. And every human heartbeat would be a small flame carried through the deepest cold the universe can offer.